The workhorse of the American space program has been this Delta rocket, with nearly 200 launches and a success rate of 90%. In fact, it was the Delta that kept the American space program flying during that period after the Challenger disaster. But all the rocket power in the world won't get you anything without information processing power, and that takes computers. Today, we take a look at computers in space on this edition of the Computer Chronicles.
The Computer Chronicles is made possible in part by the Software Publishers Association, which reminds you that software piracy is a federal offense. When a few people steal software, everyone loses. Additional funding is provided by CompuServe, by PC Connection and Mac Connection, by Byte Magazine and Bix, the Byte Information Exchange, and by Intel Corporation, Personal Computer Enhancement.
Welcome to the Computer Chronicles. I'm Stewart Cheifet, and this is Gary Kildall. Gary, I have a great picture I want to show you. Look at this. This is an actual shot taken in the Space Shuttle Discovery during its last mission. And what's interesting about that picture?
Well, it's a very complicated picture, but it looks like there's something up there in the dash.
A laptop computer sitting on the dash in the cockpit of the Discovery. Matter of fact, this laptop computer, a Grid 1530, and many people know the Grid has flown in space many times. In fact, it's interesting. There's a flight data file you need on the missions, 2,500 pages, 5 volumes, takes up a lot of space, a lot of weight. They're thinking of dumping all of that into the hard drive of the Grid and saving all of that. It's obvious you need computers in a space program, Gary. What exactly do the computers do, though?
Well, I guess we could talk about everything from payroll to maintaining parts lists and complicated systems on board and so forth. Those are real obvious. But I think the thing that's interesting is the space program really preceded our industry in a real sense because there was a need when you're putting unmanned and manned vehicles into space to bring things down in size and weight. You got to, instead of having tubes, you got to have some kind of transistorized systems or semiconductor systems. And so there's a real interest in miniaturization. As a result of that, there are lots and lots of spin-off industries, and one of them has been the PC industry.
So it's not so much what computers are doing for the space program, it's what the space program has done for computers. We're going to take a look at computers in space today. We'll visit NASA's Goddard Space Flight Center outside Washington, D.C. We'll see how they're using computers to interpret data from satellites and take a look at the hole in our ozone layer. We'll see a new robotics program where they're using robots to design the new space station. First of all, though, we visit NASA's Ames Research Center out here in Mountain View, California.
This is the surface of Mars, as it might be seen from a low-flying aircraft. The action is simulated, but the surface detail is real, assembled from a compilation of photographs of the planet's surface. It's an example of virtual reality, a means of recreating digitally an interactive model of one's surroundings, and it is likely to play a major role in NASA's plans for the 1990s.
The personal simulator allows you to go beyond workstations that sit on your desk, for example, because the workstation that's on your desk is no better than a window. But the personal simulator allows you to go through that window and be completely immersed in the spatial data. And this allows you to bring to bear all sorts of skills that you apply in the everyday world to manipulate objects directly and to explore environments directly.
The basis of the personal simulator is a digital model, or simulation of the environment. Thanks to progress in computer graphics, real-time 3D representations are now possible with adequate detail. The operator's hardware consists of a head-mounted unit with wide-angle stereoscopic display screens. Magnetic sensors determine the relative position of the headset. The images can come from a database of existing or synthetic models, or the output of a remote source, such as a television camera atop a robot. NASA expects the personal simulator to make reality more accessible to space travelers, as in the manipulation of this remotely operated robot arm. Project Director Scott Fisher calls it telepresence, or a virtual environment workstation. By wearing a glove with fiber optic sensors, the operator of this robot arm can couple his movements to those of the robot. To achieve precise control, telepresence includes voice commands and audible response, using both synthetic speech and sound effects.
Both robots to installation scale at 1/3.
Because you're transmitting this remote environment from the telerobot to the user, there's no reason you can't mediate with the computer between the two environments. You're not required to report exactly what the world looked like. You can create a synthetic world, what it ought to look like, or what would be the most beneficial task environment for the user. And so there could be a completely synthetic looking task environment which ultimately does connect to the real world.
A landing on Mars is one of NASA's major goals for the next decade, and studying the planet's surface will require new techniques that don't rely on the presence of humans. Because of the amount of time it takes for radio signals to be transmitted between Earth and Mars, it would be impractical to control the rover from Earth, a step at a time. Instead, the space agency is counting on a new kind of smart surface vehicle that can look and feel its way around Mars. These planetary rovers would be programmed to make decisions about what to examine and when.
What the situation is, if you want the rover to be able to navigate around crevices and around rocks and over harsh terrain, you have to give it some ability to sense its environment and plan around that. In addition, if you want the rover to be able to, on its own, react to these science alarms, opportunistically pick up on geological clues or presence of underground water and do some science that it might otherwise miss, you also have to build a planning system for the science subsystem. The crucial technology is building a system that will let these planners with interacting goals achieve as many of the highest priority goals as is possible.
The future Mars rover will use a kind of artificial intelligence called constraint propagation, or the ability to choose and coordinate conflicting tasks. Artificial intelligence is the key to many of NASA's latest computer projects, and perhaps the major influence in designing the spacecraft of the future.
Here at Ames, I'd say about 2/3 of our work is quite basic, advancing the state-of-the-art in artificial intelligence, and about 1/3 is applications-driven. So our projects range from very basic fundamental scientific research in artificial intelligence in fields like machine learning and machine planning, knowledge acquisition, and so on, to some fairly detailed short-term applications of those technologies to current missions.
Mission controllers will be among the first to benefit from an advanced computer interface, as old text-based terminals are replaced with graphics monitors. But the new terminals will do more than just display information in a readable style. They're intelligent assistants using an expert system to process and analyze telemetry data. Controllers then receive a clear visual representation of the spacecraft's critical systems and potential problems. NASA hopes to extend the reach of expert systems to encompass the shuttle and a future space station. Presently, shuttle-based scientific experiments must be carried out by specially trained astronauts, or the data is brought back to Earth for analysis.
Right now, we're in a situation where crew members don't have a chance to learn nearly enough about the kinds of science they're doing. We're in a situation where most experiments are relatively short-term, where data is gathered in an automatic mode and brought back to Earth for later analysis. We'd like to experiment with helping crew become more like reactive scientists would be on the ground.
One of the first expert-assisted experiments is called SHOOT, for Superfluid Helium Onboard Orbital Transfer. The SHOOT project is being developed at Ames Research Center in California to test the feasibility of refueling satellites with liquid helium. On the ground, the SHOOT software runs on a Macintosh 2 with a characteristic graphic interface. On board the space station, astronauts will view a simplified display on a laptop computer. The knowledge-based system will be responsible for the experiment's control and diagnosis. Astronauts will have access to real-time help in solving problems based on advice from the experiment's designers. Artificial intelligence is also finding applications in the design process, where the accumulated creativity of engineers is usually lost once a project is finished. A research group at Ames is creating an electronic notebook with the goal of preserving the method used by an engineer to achieve a successful design. Based on VMAX software from the Performing Graphics Company, the notebook with a memory can analyze a drawing and recommend alternatives using the accumulated knowledge of previous successful designs. NASA's experiments with artificial intelligence are still at a very early stage, but project scientists see no lack of practical applications.
NASA has just about the most interesting long-range applications of our science that we'd like to see. I mean, it's really a kick to be able to work on software that might eventually appear within our lifetimes on a Mars rover, for example. I believe we know enough about what's coming up and have made the people who are designing those things aware enough that as application spin-offs occur, we have a real shot in getting them into those missions.
When you think of computers in space, you tend to think of the massive amounts of computer power it takes to launch a rocket, or to put a satellite into orbit, or to do the complex calculations required for a rendezvous. But here at NASA's Goddard Space Flight Center outside Washington, they use their computing power not to get into space, but to manage the massive amounts of information coming back from space. To date, NASA has flown over 300 space missions, and all that research has led to tons of data. In fact, over 125,000 computer tapes. The current size of the NASA database is 6 terabytes, and the size of the database is expected to double every 2 years. So the first job for computers at NASA was to manage the immense amount of information being generated by the space program.
10 years ago, the mode of operation was if you needed to archive data at the data center, you basically drove up with a truck, dropped off your boxes of data, and then we had the job of opening each individual box, taking out the printouts, and from that printout derive the information that we need to manage the data on an individual basis. What's happening now, of course, the technology of fiber optics and high-rate networks allow us to obtain that data electronically.
But with a database this size, and with users scattered all over the world, the real software challenge was to not only speed up the process of accessing information, but to create a user interface that could handle such a variety of needs. The answer was a database management system with a heavy dose of artificial intelligence. It's called IDM.
This completely hides from the user any knowledge that he has to have about the internal structure of the database or any knowledge that he needs concerning the actual querying of the data set. And he discusses or converses with this intelligent front end in English. So in actuality, I've seen a session for which you can sit down and talk to this intelligent data management interface. It will generate all your queries. In fact, I've seen it sometimes in just a few sentences. You can ask it a set of questions for which it would generate 100 lines of code, and that's what's issued to the database management machine, and then the results are brought back.
One of the most popular databases at NASA is TOMS, the Total Ozone Mapping Spectrometer. This database not only provides data, but stunning graphic images of the growing hole in the Earth's ozone layer. In these images from NASA's Nimbus 7 weather satellite, you can see in blue the gap in the Earth's ozone layer over the South Pole. These processed images use color and shape to further dramatize the ozone problem. This terminal is accessing images from IRIS, the infrared astronomical satellite. It uses complex image manipulation to show an inverted view of the galaxy so as to study the stars and their infrared radiations. NASA's Space Science Data Center is a huge network with some 13,000 terminals worldwide. It's a relatively open network, and so there is the concern these days over the damage that could be done to the network by a computer virus.
Viruses, like our new computer technology, is a fact of life. We have to, and we have looked over our systems to examine where are software loopholes or whatever that would allow for a virus to grow and propagate. And based on our knowledge of that, we've taken action that is still in line with what we call that acceptable level of security, that balance between ease of use and difficulty in getting into the system.
The other obvious concern at NASA is security. One of their databases, called SPAN, the Space Physics Analysis Network, was recently broken into by some hackers. But Jim Green says he's not too worried.
SPAN is a network that has existed now for about 9 years. And even in the early 80s, we had individuals that were doing hacking or unauthorized access to the machines that are a federal resource. We have set up for many years a structure that allows the detection of those unauthorized accesses, the collection of information, and then that information is turned over to the appropriate authorities.
So the message is you may break in, but you'll also get caught. One of NASA's most complex satellites is due to be launched at the end of 1989. It's called the Hubble Space Telescope. The satellite is the size of a Greyhound bus, and it will be the most sophisticated observatory ever put into space. But despite its sophistication, its computing power is minimal.
There are actually two small computers on board, both of them using very antiquated technology by popular standards. And the reason for that is that it is so expensive to qualify equipment for space flight that this takes a long time, and the advances in computer technology move much more rapidly than our ability to qualify things for flight. The equipment we have on board was selected when the project started in the late 1970s, and that equipment had been space qualified before that, so that it is really sort of early 1970, late 1960s technology that we're flying.
That means the satellite itself is not very intelligent.
The only kind of decisions it takes on its own is if it detects that it is going unstable and is slewing towards the sun, say, then it will take protective action, because if it looked at the sun, it would destroy itself. But except for extreme safety concerns like that, everything is predetermined and pre-directed from the ground.
The good news is that the computers on board the Space Telescope, or HST, are modular. All the major subsystems are made up of plug-in black boxes so that they can someday be upgraded.
This is the first satellite that has been designed from day one to be serviceable in orbit. And so while we are starting out with a computer that's already old, as new computers become qualified, we will be able to take them up and let astronauts take them up and replace the computers up there with new updated versions.
While the computing power on board the HST may not be much right now, the ground control system is the most sophisticated computerized system ever assembled for a satellite. And one of the features of the Space Telescope Operations Control Center is its emphasis on non-specific hardware.
This is the first satellite that I'm aware of which has relied so heavily not only on computer power but on a database management concept. All the variables that we know of, that we have control over and may want to change, are maintained in a large database. And rather than building in parameters into hardware or into operational capability, the entire satellite basically is database driven.
The biggest computer problem that faces the Space Telescope project is the massive amount of raw data that has to be sent to Earth and the 1 megabyte limit on available bandwidth for transmitting that data.
We're going to be forced to do onboard data processing and send back only the analyzed data rather than the raw data. That'll be an agonizing sort of thing for a scientist to face. Scientists always want to look at their raw data and see every nit and every imperfection and deal with it themselves. But we just do not have the bandwidth in communications to make that still be possible in the future. So one of the first things that I would like would be a VAX on a chip, say, that was space qualified that I could put up there.
If there is one overriding computer theme at NASA, it is this need to get more of the computer.
Quite a bit of work on this.
That is certainly one of the issues in the FTS program, where NASA engineers are designing perhaps the world's most sophisticated robot, the Flight Telerobotic Servicer. NASA is due to launch its most ambitious project ever in 1991, its first ever full-fledged space station. And there's only one way to do that: ship it up to space in pieces and assemble it in orbit. And there is only one practical way to do that: with robots. And that means lots of computer power.
5 years ago, we would not have been able to do very much meaningful interpretation in the robot realm, but the computers available now are capable of inputting all the necessary data so the robot can do very meaningful work. In other words, it can input in real time sensory perception, looking at video inputs from cameras mounting on the robot wrist, force torque sensors mounted so you can get reflected force, or meaningful data coming back from more than one source, so that not just to control the robot, so the robot can control itself.
Computing power is needed not only to drive the robots, but also to create graphics simulation models so that robot problems can be solved before they happen.
We are capable now of doing graphic simulations of what the robot will perform as a function. You can look at the overall capability of where the robot can reach, where the lighting should be, where the camera angle should be, where the operator would be in relation to the robot before you ever start to assemble it in, for instance, the shuttle bay. And these are not these graphic representations are mathematically accurate. They're actually models, and you can see when the robot can or can't reach a thing, when it would reach a singularity in its ability to get somewhere, and then you would move one thing or the other before you ever get there and find out that you have confronted with a problem you can't resolve.
This simulation using silicon graphics software is helping the computer engineers here design this gantry robot to be used in constructing major components of the space station. It has 6 degrees of freedom and can lift up to 4,000 pounds and position it with an accuracy of 1/10 of an inch. It is the most sophisticated gantry robot in the country, yet all the robot research work which has gone before is not much help in designing this robot.
First off, your whole scenario can't depend on gravity. Normally, you just put something together, gravity would help you pull it together. When you put something together in space, as you touch it, it just repels. If you were to have a gripper that didn't close around something and it were to let go, it would actually be a projectile if it had any momentum at all. So all the things we're confronted with in that manner require specific space-oriented hardware. End effectors and grippers, things used on the Earth, just will not be meaningful.
EVA, or extravehicular activity, is the most costly and risky activity in space, and so the engineers here are creating this robot to extend the reach of the astronauts' own arms and hands. This elegant robot has 7 degrees of freedom in each arm. It is tele-operated by an astronaut, either on board the spacecraft or even from the ground. But here again, the major computer challenge is finding the computer power and reliability so that the real processing capability will be up in space and not on the ground.
If you had terribly time delays between space and ground, you would like to send up a high-level task, find the box and move it. And then the robot would have to have the computational power to decide what that meant, how it would plan the task, how it would plan the path doing the task, and the compute power then would have to reside in space so that you would eliminate the time delays. If in fact you were in space and were teleoperating the robot, then you would be right in proximity with the robot, and the compute power could be either with the individual, say in the shuttle teleoperating it, and the robot right outside in the shuttle bay, or even on the space station.
Despite the massive computer power assembled at the Goddard Space Center with its many mainframes and minis, the system's designers here know that for any computer system to be functional these days, it has to work in the new environment of the personal computer.
So what we're trying to do is to adapt to that environment. The systems we have per se certainly go far beyond what the processing capabilities of a personal computer, but we certainly see that that's the user interface, and our ultimate customer is the one sitting at their personal computer.
In the random access file this week, Lotus has started shipping 123G, the newest version of its spreadsheet program designed for the OS/2 Presentation Manager environment. 123G features GraphTool, a set of new graphic capabilities, including a gallery of graph types used in an icon-based user interface. 123G also features a WYSIWYG windowed environment. The scene was San Diego, not Hollywood, but the stakes were just as high as the Software Publishers Association handed out its annual Excellence in Software Awards, the computer version of an Oscar. The biggest winner was a game, SimCity from Maxis. It won top honors for Best Simulation Program, Best Entertainment Program, and Best Curricular Program. Winners in the business software category included Lotus Notes and Lotus Magellan, Quattro Pro, and ThinkC. Winner for the Best Personal Productivity Program was Quicken. Where in Time is Carmen Sandiego won for the Best Home Learning Program. The Best Technical Achievement Award went to Real Sound from Access Software, and the Best Design Achievement Award went to Hewlett-Packard's New Wave. Britannica Software has announced that its award-winning Compton's Multimedia Encyclopedia will be bundled with Tandy's new 2500 XL PC. The new Tandy computer comes with an internal CD-ROM drive. The Compton's Encyclopedia features the full 26-volume print encyclopedia, plus 15,000 pictures, 60 minutes of sound, and a search and retrieval function, all on one 5-inch CD-ROM. Taking a look at this week's best-selling software for IBM compatibles, according to PC Connection, there is a new #1 program this week, Expanded Memory Manager 386 from QuarterDeck. #2, also from QuarterDeck, QRAM. TurboTax drops to #3, followed by another QuarterDeck product, DeskView 386 and WordPerfect. Rounding out the top 10 are Microsoft Windows 286, Quicken, PC Globe, Andrew Tobias's Tax Cut, and Procom Plus. Microlytics has announced a new software product called Inside Information. It is a backwards dictionary, and it's being touted as the first new classification system for the English language since Roget developed the thesaurus 100 years ago. With Inside Information, you type in a definition, and the program comes up with words that satisfy that definition. Finally, DataDesk has come out with a new computer keyboard that has separate movable modules for the typewriter part, the numeric keypad, and the cursor keys. So left-handers, for example, can put the keypad and cursors on the left side of the keyboard. DataDesk says they will also be coming out with a modular trackball for their keyboard. It's called the Switchboard. That's it for this week's Chronicles. I'm Maria Gabriel.
The Computer Chronicles is made possible in part by CompuServe, which offers online information related to today's subject. Members type Go Chronicles. Non-members call for more information. Additional funding is provided by the Software Publishers Association, by PC Connection and Mac Connection, by Byte Magazine and BIX, the Byte Information Exchange, and by Intel Corporation, Personal Computer Enhancement. For a transcript of this week's Computer Chronicles, send $4 to PTV Publications, Post Office Box 701, Kent, Ohio, 44240. Please indicate program date.